Welcome back to Chapter 4, Part 8. In this part, we will study multiple regression. Regression models that use more than one explanatory variable to explain the variation and the dependent variable are called multiple regression models. Okay, so it looks like this. Y, dependent variable, is a function of, right, parameter A, b times x. We had x before, but now we have other explanatory variables, c times w and d times z. So here the independent variables are these now. It's not only x, but we have x, w, and z. And we are trying to find the coefficient estimates for a, b, c, d hat, and as a result we can get yi hat. Okay, coefficient for each explanatory variable or independent variable a, b, c, d, right, measures a change in the dependent variable y associated with 1 unit change in that explanatory variable, holding all else constant. Okay, so one special model is quadratic regression model. Quadratic model is a nonlinear regression model. Okay, so do you remember the very first example we studied? C equals a plus b, right? X quantity, this was quantity, plus c q raised to the power 2, blah blah. So this is a quadratic model. We're looking at the impact of quantity produced on cost, but also how increasing quantity, is it having an increasing impact or a increasing impact on the total cost of production. Okay, so that's why we do estimate quadratic models, because this independent variable enters the model as x raised to the power 2. Okay, we use when curve fitting scatter plot that is u-shaped or upside down u-shaped. Okay, you have to do a linear transformation to compute the new variable. So you need to call a new variable z equals x raised to the power 2 to be able to actually work with this model. Why? Because this model, this regression model, ordinary least squares or minimum least squares, minimum squared residuals model assumes that all variables are linear. However, this x raised to the power 2, therefore we have to change this x square and call it a z. Okay, so instead of this, we are going to estimate this model. Okay, so here's an example. Y, x, and z, right? Y is given, x is given, z is nothing but x raised to the power 2. So you grab the x column, find the values for x raised to the power 2 and use these values in the regression. Okay, so this happens when the relationship is, for instance, u-shaped. This is an example of, for instance, average cost curves. So this model, again, I'm going to give another example. For instance, y and x, and this is the, right, x is quantity produced, y is the profit function. Profit function, folks, looks like this. We're trying to, find this maximum point. That's for a future chapter. But let's say quantity and profits, the relationship looks like this. This is not a relationship that you can draw, downward sloping line or upward sloping line. Okay, so the line that best fits there, this is not actually a line, but it is a upside down u-shaped curve. This is an example of a profit function. So in this case, what you have to do, profits a plus b quantity plus c quantity raised to the power 2. So I'm going to call this a new variable z, right? Whatever you can call it, I'm just going to call it z. Q raised to the power 2. Instead, I'm going to plug in z value. This is how we do it. Okay, let's talk about log linear regression models. So log linear regression model takes this form. Okay, so y equals a x raised to the power b, z raised to the power c. Okay, so in this case, b will give you the percent change in y divided by percent change in x. So this is really, really interesting. B directly gives you elasticity. And C will give you percent change in y divided by percent change in z. Okay? So what we do is we transform this by taking natural logarithms. If you are not familiar with logarithms with the e base, right? These are called ln, natural logarithms. So I'm just going to give you an example. Logarithm of this, you put log e. This is basically equal to ln, right? You take the logarithm of this expression. Ln y equals ln a x raised to the b, z raised to the power c. Okay? So when you have this kind of expression, you have multiplications, logarithm operators. You can separate them by addition. Ln x raised to the b plus ln z raised to the power c. One more step. Whenever you see a power, logarithm operator pushes it as a coefficient. So ln y equals ln logarithm of a plus b ln x plus c ln z. So this is basic logarithm operator. This is 7th grade. If you are not sure about your knowledge, please go ahead and Google search, natural logarithms. It will take you 5 minutes to learn. Okay, so instead of y equals ab blah blah, you got these logarithms of certain variables. So instead of a, you have logarithm of a, and we are going to do the same transformation. All right, so I'm going to get rid of everything. All right, so you're going to see this exact transformation. B and C will be elasticities now, as I mentioned before. B will be percent change delta, and economics is used for change. Percent change in y divided by percent change in x. It's going to be x elasticity of y. Okay. C is going to be also percent change in y as a response to percent change in z. Okay, so remember, in regular linear models, y a plus b x, b was simply delta y divided by delta x, right? Here this is percentage change, which is elasticity. If you are having trouble with elasticities, there are some chapters dedicated to that in our book, and go review those concepts. Okay, so log linear regression, for instance, this is an example of a y hat 63575 x raised to the power negative 0.96. So sometimes you may see this shape relationship. This is an example of, for instance, you have costs here, average total cost. Actually, I'm not going to do average total cost. I apologize. This is the shape of average fixed cost, and this is quantity. So average fixed cost exactly looks like this, average fixed cost. And we will learn about average. Don't worry about it for now. Fixed cost definitely has this model. So you can transform it by ln y equals, right, ln a plus b ln x. So in this case, what you see, this b here is negative 0.96. Okay, so that's pretty much it. So sometimes the relationships will have this form. In some cases, for instance, in the case of average fixed cost curve, you will see this kind of declining relationship. Therefore, we have to use log linear regression model. Okay, so the last one is the log linear regression. So this is, this is the shape. However, if you do transformation, right, you're going to be able to fit it as a linear line. So don't forget that. You do the transformation, but you need to, in order to get those values, you need to make sure to go back to the original equation. All right? So that's it, folks. Go over these summaries of this chapter, and I'll see you in the next unit.